Hello and welcome to this next lecture on acoustics. Today we will be looking at wave equation in 3D rectangular Cartesian coordinates. So the equation looks like this: del 2 p tilde del x square plus del 2 p tilde del y square plus del 2 p tilde del z square is equal to 1 over c square del 2 p tilde del t square. Okay. We will be looking at a rectangular box, okay, in Cartesian coordinates. These walls are rigid, okay, walls are rigid, and it is going to be driven by some initial conditions. The sound field inside will be driven by initial conditions. So we will look at this situation, okay, and so we start by the method of separation of variables. So the p tilde x comma y comma z comma t is going to be given by sum x of x, sum y of y, sum z of z, and the time. Okay. So if we now substitute this, we have seen this earlier also, separation of variables. So the x acts on the function which has only x, y derivative acts on the function that has y in it, and so on. So what we will get is x double dash by x. By double dash we mean x differentiated twice with respect to its argument. Okay. Similarly, y double dash of y means y differentiated with its argument y, this y differentiated by its argument twice, plus z double dash by z of z, okay, is equal to t double dot by c square into t. Okay. So now what we will say here is that x, each of these, okay, I will give it a number minus kx square, minus ky square, minus kz square, and equal to minus k square. Okay. Why? Because this is purely a function of x, it's purely a function of y, it's purely a function of z, this is purely a function of time. So this is, I am going to equate it like this. So this is equal to minus k square. Okay. The negative and k square we have understood before. Okay, this has to be a negative real number. If it's 0 or positive, it will have unnatural behaviors. Okay, we have seen this before. So essentially kx square plus ky square plus kz square is equal to k square. Okay. Now we will take up each of these individually. We will take up each of these individually. So what we get first for x, x double dash of x plus kx square x of x equal to 0. Okay. So, this is like a simple harmonic oscillator, except this is in space, and these sort of problems are called Sturm-Liouville problems. Sturm-Liouville, L-O-U-I. Please don't quote me on the spelling here. Okay. Sturm-Liouville problems. Very interesting set of problems of ODEs in space, boundary value problems. Okay, and very beautiful theorems. So, now this has a standard solution, which is A cos k x x plus B sin k x x. Okay. And we have a rigid walled condition. This whole box is rigid. Okay, we have a rigid walled condition. What that means is this x at 0, the derivative x dash at both x equal to 0 is 0, and x dash at x equal to L is equal to 0. That is what it means. Okay. Rigid walled means velocity is 0. Velocity is 0, that is rigid walled. Velocity is 0, and velocity is proportional to del p del x, and therefore del x or dx, hold on, dx d capital X of d small x by d small x, which is x dash. So, x dash is 0 at x equal to 0 and x equal to L. So, let us get to x dash first. X dash is equal to minus a k x sin k x x plus b k x cos k x x. So, if we set x dash of 0 is equal to 0, that means this is 0 anyway, that implies b is equal to 0. Okay. Therefore, my x of x is equal to a cos k x x, because b is 0, then x dash at L, okay, that gives me minus a k x sin k x L equal to 0, which means sin k x L equal to 0, which implies k x L is equal to, we will call it m pi. Okay. M going from 1 onwards, because otherwise it is a trivial solution, which means k x is equal to m pi by L. Okay. So, now we will have to do something more. So, let us say this is my x direction, that is my y direction, and this is my z direction, and I have dimensions Lx, Ly and Lz. Okay. So, x dash at Lx, so kx Lx, this is by kx Lx. Okay. So, I have found a kx. Okay. So, this is an eigenvalue problem. Okay. This eigenvalue is m pi by Lx. Okay. So, that means with this box with rigid walls likes only a certain set of kx's, not every kx is admissible, that is the eigenvalue. Okay. So, now similarly all other forms are same. Similarly, if I do it for y, I will, okay, just before so what is the shape of the function x of x? b was 0. So x of x is a cos m pi by lx into x from here. Okay, b was 0. Okay, so that's the shape in the x direction, and this is the eigenvalue. So this is a mode shape in the x direction, mode shape or eigenfunction, mode shape or eigenfunction, and this is the eigenvalue. Okay. Similarly, for the y direction, okay, so I will get I will choose another set. So let us say for y I will get okay, let me do this. I will call this ax. Okay, I will call this ax, bx and so forth, ax, bx, otherwise I will very quickly run out of alphabets. Okay, y becomes a y cos of n pi by l y into y, again n going from 1 onwards. Okay, actually n can go from 0. Yeah, and m can go from 0. M can go from 0. Okay, that will give the constant pressure. So n can go from 0. Okay, then z. So this was, sorry, this was y of y, and this is z of z. Is equal to a z cos mn, I will call it q, q pi z by lz, and here also q can start going from 0 onwards. Okay. So now, so I have this equation that I derived earlier, which is important, this one. And what did I find? Kx's are not unique, they are a set of numbers, similarly ky and kz. Okay, so kx's are a set of numbers, so will kxm's, right, those are m pi by lx, then kyns, they are n pi by ly, and we have kzq's, which are q pi by lz. Okay, and so we have kxm squared plus kyn squared plus kzq squared, and we have k squared over here, but now that has m and q indices. Okay, so this has to be satisfied, Now what does that tell me? This k m and q is omega square m and q by c squared. Okay, so therefore this gives me the equation for the natural frequency. Equation for the natural frequency. Okay, what is that? Omega square m and q by c squared is equal to, let's see, m pi by Lx whole squared plus n pi by Ly whole squared plus q pi by Lz whole squared. Okay. So c square I will bring on top, c squared I will bring on top, this entity remains here, and then I want to get to omega mn q. So I take a square root of the whole thing, which ends up as c square root of this squared plus this squared plus this squared. Okay. Then I want it in, this is radians per second, I want it in hertz. So divide by twice pi, divide by twice pi. So I get f mn q in hertz. Okay. So I didn't want to repeat, so let me write it once now that we have it. The f natural frequency in hertz or cycles per second is given by c by twice pi square root of m pi by Lx whole squared plus n pi by Ly whole squared plus q pi by Lz whole squared. Okay, that's the. Now what is the solution? We said the solution p x comma y comma z comma t. Okay, so we'll have to look at t also. Let's just do that. We didn't see t also. Okay, so what did we end up with? We had t, let's see, t double dot plus k square t, t double dot plus k square. Now k square is k square mn q, right, into c square is equal to 0, and kc is omega. So t double dot plus omega square mn q into t is equal to 0. So that my t of t is equal to a cos omega mn q t plus b sine omega mn q t. Okay. So I have all the, I have x solution, I have x solution, I have y, I have z, and I have t. So if I now put my solution together, x, y, z, comma t, I will get ax m cos m pi by Lx x into a y n cos n pi by Ly y into a z q cos q pi by Lz z into let me say a let me say m and q cos omega m n q into t plus b m n q sine of omega m n q into t. Now these constants can be absorbed in here. in here, and I'll rename them as the same name. Okay. So now my phi m and q, which is the spatial mode shape of x comma y comma z, is cos m pi by Lx x into cos n pi by Ly y into cos q pi by Lz z, and this is the mode shape, m n qth mode shape, m n qth mode shape. All three terms together represent one mode shape. Okay, and it has this natural frequency. Okay, so this is the mode shape. This is the mode shape, and that is its natural frequency in hertz. Okay, and this is the solution. So we write now the total solution, because there are there are infinity of these, and infinity of these. So we have to sum that up, because each of those is still a solution. Okay, so now my single index pressure is given by cos m pi by Lx x into cos n pi by Ly y into cos q pi by Lz z into a m n q cos omega m n q into t plus b m n q sin omega m n q into t, and the total pressure, so I'll call this phi m n q. So the total pressure P x comma y comma z comma t, I'm not putting the tilde because the whole thing has turned out real. Okay, so it is summation over m running from 0 to infinity, summation over n 0 to infinity, summation over q going from 0 to infinity, phi m n q, which is spatial x comma y comma z, and this is temporal a m n q cos omega m n q t plus b m n q sin omega m n q t. Okay, so that's the total response. What are we trying to do? What are we trying to do? We have, just to remind ourselves amidst all this expressions, we have a rigid walled box. Walls are rigid, and there is a acoustic space inside, air inside. Okay, and it is driven by an initial condition. That means at time t equal to 0, there is some pressure and then some pressure derivative. Okay, and from there I am going to measure what's going to happen. From there I am going to figure out what's going to happen, and this is what is going to happen. Okay, and so the unknowns are unknowns are A, M and Q and B, M and Q. We got to figure that out, okay, based on the initial value problem. Okay. So, here is the initial value problem. Initial value problem. Okay. The initial value problem is this. I have the same system and the pressure throughout the box at time t equal to 0 is some value P0 x comma y comma z, and the derivative of the pressure at everywhere in the box at time t0 is another function p dot 0 x comma y comma z. This is the initial condition at time t0. Okay. Now the box will start responding to this, or the dynamics will evolve from here onwards. These are the conditions given. From these conditions I have to figure out my A, M and Q, B, M and Q, and once that is figured, this solution is known. Okay, that is the whole. So now there are theorems on these eigenfunctions, their properties, they are orthogonal. These eigenfunctions are orthogonal, okay, and they also have a completeness property, completeness. Okay. So we will not get too much, this is not the course for this. Okay. So we will use these two properties of the eigenfunctions. These are the eigenfunctions. Okay. We will use these two properties of the eigenfunctions to find out these constants A, M, N and B, M and Q. Okay. So now in accordance with this first condition, time t equal to 0, at t equal to 0, what is my P? I will use to this complex x comma y comma z comma t at 0. That is this triple sum. I will just put one sum M and Q, then phi M and Q, and time t equal to 0. So this is 0 anyway and this is 1. So I get A, M and Q. Okay. So this is the left side, and the right side is given, it is equal to P0 x comma y comma z. Okay. Similarly, at time t equal to 0, del P by del t x comma y comma z at t equal to 0, what is that? That is going to be a derivative of this with time. Okay. So if I differentiate, I will get an omega m and q out here and a minus sign, omega m and q out here and a cosine with a plus sign. Okay. So this becomes cosine, that becomes sine. At time t equal to 0, this is gone. Okay. So this remains. So what I have is del p by del t at x comma y comma z at t equal to 0 is a triple sum, mind you, of phi m and q, omega m and q and b m and q. That is given as p dot 0 x y z. Okay. I have this, let us call this 1, let's call this 2. Okay. So these BMNQs and AMNQs are my unknowns, they are coming under this infinite sum. Okay. So I am going to use the orthogonality of these functions. Okay. So what does the orthogonality say? If I orthogonality, let me write that. Orthogonality says if I have an integral 0 to Lx, 0 to Ly, 0 to Lz of phi mn q, phi, let's say RST, dx dy dz, that is equal to gamma, let's say gamma mnq, if m is equal to r, n is equal to s, okay, and then q is equal to t. It is 0 otherwise, else it is 0. So this index has to be equal to this index has to be equal to that index, this index has to be equal to this index, and if you integrate you will get a non-zero constant. If any of this is a mismatch, then it is a 0. So that is the orthogonality condition. Okay. So if you, so now how do we do this? So we have summation or mnq phi mnq a mnq is equal to p0 x comma y comma z, and then summation mnq phi mnq omega mnq b mnq is equal to p dot 0 . So I multiply this by sum phi RST let me make some room here. Is equal to p0 xyz is equal to p dot 0 xyz. So what I do is I multiply this by phi RST dx dy dz and I integrate over the volume. Similarly here also I multiply by phi RST dx dy dz and the integrate over the volume. Volume being 0 to Lx, 0 to Ly, 0 to Lz, it is a triple integral. Okay. Now provided m index matches r, n matches s and q matches t, there is a non-zero value. So then I get the integral equal to gamma mnq a mnq is equal to, I have to do the same on this side which I forgot, integral over a volume phi RST dx dy dz integral over the volume phi RST dx dy dz. So this becomes equal to integral, let me explicitly put it, Lx Ly LZ P0 phi RST dx dy dz, and therefore AMNQ is this integral. I will not repeat it, by gamma MNQ. Okay, and by the same logic, BMNQ is this integral 0 to Lx, 0 to Ly, 0 to Lz P dot 0 xyz phi RST dx dy dz divided by gamma MNQ omega MNQ. So now AMNQ, BMNQ are known, and once you substitute back, AMNQ is known from here, BMNQ is known. Once you substitute back, this is the response. Okay, and the response will be at all these frequencies, omega MNQ frequencies. So what physically it means is that if I have a box, rectangular box, and there is air inside, and there is some initial conditions given, some condition is given, then this box will respond in the sound at an infinite number of frequencies. Okay, and the response will be the sum of all these frequencies. So I'll close the lecture here. We'll continue. Thank you.